So we're really happy to have him, and we're gonna listen to his talk about machine learning and in general the Bayesian analysis and those methods and how they apply to nuclear physics. So thank you, and you're gonna start.
Thank you so much, CB, especially for the invitations, and thanks everybody for being here. Can everybody hear me okay? Okay, if at some point you cannot, you let me know. You can interrupt me, and then I will try to scream louder. So my talk is titled Life is Too Short for Slow Computations, and I'm going to be talking about a lot of stuff, but the main aspect of the talk is going to be about something that is called dimensionality reduction, and that applies to many things, in particular making computations faster. Now, it is kind of ironic that in a talk that is about reducing the dimensions, I have 174 slides, but two disclaimers on this. The first one is regarding to those materials. I'm going to finish at 45 minutes, no matter what. So if we take some time discussing part of it, I will just go through the last part, which is the important part that I want to mention. I will not pin you to your seats for longer than we need to. The idea of this is for the slides to be part of a material that you can take a look after. If anything resonated with something that you can apply it to your particular research, be it in nuclear physics or otherwise. So those are the link to the slides, and I'm going to give the same QR code at the end, and I'm going to make sure that the slides and the recording, because I'm recording the presentation, reaches CB and he can share it with everybody so that if you want to watch it again, or if you have somebody that was not able to come but they could watch it, it's useful for them. That is my first disclaimer. My second disclaimer is that this goes especially for students. You're going to see a lot of results and a lot of things. I didn't do all of this by myself. So if you're sitting there and feeling like, oh, I only have one paper and I'm in my X year and blah, blah, blah. No, that is okay. We all have our own path towards our academic careers. And the main reason why I'm allowed to do all of these things is not by standing on the shoulders of giants, but rather by holding hands with a lot of people that are very, very smart and know what they're doing. So this is the outline. I'm going to motivate what we do in nuclear physics. This is a colloquium, not a nuclear physics seminar. So I'm going to give you some ideas. Then I'm going to be talking about the dimensionality reduction approach, some main ideas on how this works, and I'm going to shower you with applications. We're going to go fast through those. And I want to end the presentation with a very important thing that relates to how we can use these tools to create more points of entry for a broader community in science, for people that are usually not represented or don't have the same amount of resources as others to join us in the scientific endeavor. So, nuclear physics this says in 3 minutes, but it may take us 5 or 10. The broad idea, you have an atom, and if you're aware of an atom, you will know that there is a nucleus in the center and a cloud of electrons that is floating around. And depending on how many electrons your atom has, we will call them a different name. This is an updated periodic chart. That is an outdated periodic chart, but as we continue to discover more protons, we put more electrons, and then we are allowed to name these things in funny ways. In nuclear physics, most of the time, we don't care about the electrons. I'm going to only be focusing on the center, which is the nucleus that is made out of protons and neutrons. And we characterize that by N, the number of neutrons, and C, the number of protons. You can arrange the new information that you get once you start thinking in terms of the extra degrees of freedom, which are the neutrons, in what is called the nuclear periodic table. And in this nuclear periodic table, I could still talk about an element, for example, carbon. I will call it carbon 12 because, as my marbles in here, this carbon has 6 protons. That's why it's called carbon, but it has 6 neutrons. That's why it's 12. It's a total of 12 marbles that makes this particular isotope. You could zoom inside the nuclear periodic table and you will find our friend carbon 12 sitting there. But for a given element, carbon, I have an entire line of different types of carbons that I could have. Ones that have more neutrons, ones that have less neutrons. These are called isotopes, and the thing that I and the people that I usually play with are most interested in are not the relatively boring ones that are the stables, the ones that are shown in black, but rather those that you obtain whenever you get very far away from the stable ones. Those are called the rare isotopes. And because they're so interesting to study, and there's so many things that we can learn about them, we have created a specific building, which is called the Facility for Rare Isotope Beams, to study these rare isotopes. That is in the middle of nowhere in east of here. in a city called East Lansing. But the way that I see that is basically as if we have built a ship to go and be able to explore these new territories that nobody else has been able to access before. Now, if you're feeling a tingle of interest about this particular facility, and more important, the people that are around the facility, there is a documentary movie coming out by the end of this year, hopefully, that tries to highlight that, how this facility operates and the people that are around them. And here's a QR code if you want to see the teaser of this movie that the director and physicist, Agnes Moxie, is presenting. So once that you have set up your visions in nuclear physics, there's a lot of interesting things that you can do. And let me break this down in 4 topics, 4 types of interest. I could be asking big questions about astrophysics. For example, where do all the heavy elements come from? If you think in terms of fusion, after you start merging hydrogen and helium and then carbon and oxygen inside a star, eventually the star gets bored once you reach iron and nickel. So if you wanted to create all of the heavy elements, there has to be a different process that created these elements. That is one of the open questions that we're studying at EFRIP and in other places. Questions regarding structures. If I get very far away from the stability line, the isotopes that are stable, what type of shapes I'm going to find? What is going to happen with all the shell structures? Shell structures, by that I mean that the nucleus is more like an onion than it is like a bunch of grapes. So usually protons and neutrons are arranged in layers, in shells. These shells will change depending on where on the nuclear periodic table you are. Questions about neutrinos and symmetries. What's up with neutrinos? They're just weird. There are many things that we think that we understand about them, but there's some unconstrained. For example, are they their own antiparticle or not? There is a big effort towards experiments that try to measure this. Those are called neutrinos-less double beta decay. And if that is possible, that will hint that these two are, that the neutrinos are their own antiparticles. We do not know. There is a lot of nuclear physics that needs to go in there to be able to make these experiments. And finally, the reason why we sell to the public that they should keep giving us funding, can we make anything useful out of all of these things that we're studying? Once you have settled on these type of big questions, if you want to answer them, it is really, really hard to study. And I'm going to break 2 reasons because of that. The first one is that the rules of the game, if you want to think in terms of a game, are very unclear. By that I mean, as a theorist, you might want to say, oh, I want to write my Schrodinger equation with my Hamiltonian that will tell me how my protons and neutrons are going to interact. But the problem is that the rules are not very easy to grasp, and whenever you try to connect with experiments, it's similar as if you were trying to understand the rules of chess just by looking at 2 people playing chess, and you can only watch one instant at a time every time that your experimental friends heroically go and measure something, and it's very dark, so you actually don't see very well what is happening. And half of the screen doesn't work because neutrons don't like to interact electrically with things, so you can only watch what the protons are doing most of the time, and you're wearing sunglasses. So this is how doing nuclear theory and trying to complement with experiments feels like. The second aspect is that even if you have the rules of the game figured out, the emergence of complexity is something that is going to come and bite you. This is an example that I want to make with the game of life, which is a game that has very simple 3 rules. It's about whatever cells in an infinite grid can be alive or dead. And this very simple set of rules can give rise to incredible complexity. There is no way that you will be able to predict that this is something you could build with these 3 rules. So even if you have the rules figured out, there will be complexity that will be beyond of what your computational models will allow you to reach. So because of all of this, in my view, it's just a wonder that any of the things that we're studying and the models that we're using to predict things even work a little bit. For that to make it better, we do need a very strong theory experiment observation cycle. And let me give a specific example of how that will look. We are at EFRIP. This is a nuclear chart of protons and neutrons that you can access. We're interested in all of these things, and I'm going to focus in one of them. Let me focus in astrophysics. Let's say that in astrophysics, I really want to understand the rapid neutron capture process. That is this process in where we're trying to model how heavy elements could be formed. If you want to understand that, you will need data and predictions from theory for a lot of nuclear properties. Let's say lifetimes, beta decays, capture rates, and nuclear masses. So if I want to use calculations of nuclear masses, I have a lot of theoretical models that I could use. If I grab 2 of those models and I run the same R-process calculations, which is basically estimating how much stuff of each isotope you get, I already get different answers. So then I say, okay, let me try to grab some of the experiments that I can make on all of the isotopes that I could choose to try to constrain these theoretical models. There is a lot of them to choose from. And not even that, if you now want to connect with the people that are doing observations in astronomy, like measuring gravitational waves or the radii of neutron stars, you have a lot of things in your plate. And if you want to make this cycle go along, my point is that you need to do a lot of statistics and machine learning. And that is what is going to motivate the rest part of the talk. Let me put you two interactive examples on why this makes sense. This is an example on why statistics, why knowing statistics can help you make decisions that are informed, but rather than just randomly moving across things that you could do. How many of you have heard of the Monte Carlo problem? By show of hand. Okay, I see many, but I see some of you that haven't. Those who have, please abstain from answering the question that I'm about to ask. Those who haven't, imagine that you are in a show in where the host of the show tells you, I have 3 doors, and behind one of the doors there is a golden ticket for an NSF proposal that will just go directly. You will have funding to do your research, no questions asked, whatever you want. You really want that golden ticket. But behind 2 of the doors there are goats. So you choose one of the doors at random, and then the host tells you, I'm going to show you that in door 3 there was a goat. The question is, should you change doors or keep with the door that you were chosen at the beginning? You have 10 seconds to think about this. Sorry?
Yes, I need to do the door.
You should treat the door? That's what you think. I'm going to give more seconds to the rest of the people. Okay, by show of hands, how many of you will change doors? And how many of you will stay on the same door? Turns out, if you run the calculation, if you change doors, you have twice the amount of chance of getting the NSF golden ticket. You see how such a decision, if you base it on actually running the calculation, and I know it sounds very anti-intuitive, we can discuss it in detail further, but this is the point that I want to make, that it is very important that these decisions come from an informed way of reasoning. Now, for those of you that said that you knew the problem, this is an extra question. What happens if the host didn't know that there was a goat when they selected? Does that change anything on your reasoning? Don't think about it too much because I want to move to the next thing, but we can discuss it afterwards. Example about machine learning. Now, my next question is for you to think, without thinking in terms of neural networks and all the new computational tools that we have available. If I were to ask you 40 years ago, you have basic programming, Fortran, and I want you to be able to write a Python package or a Fortran code that is able to distinguish between the different digits. How would you even write something that is able to do that without neural networks? You have 10 seconds to think as well. Probably no idea. Let me show you how I do it in today's state. I go and I ask ChatGPT, could you download the means data set? Could you use TensorFlow to train a neural network for classifying the digits? And can you show me the performance of the network that you train? And ChatGPT is like, sure, of course I can do that. That is very easy. This is a code that ChatGPT provided. I run it, and here is my classification. And it runs perfectly smoothly and well, and I didn't even have to think. Now, I'm not claiming we need to use ChatGPT to do research in general, but the point that I'm trying to make is that there is a lot of tools available that could propel the way that we do scientific endeavors, and I'm not the only person saying these things, that are beyond of what you might have think beforehand. And that's the thing that I want to motivate, that for things like nuclear physics, and I will argue most of the research endeavors, this experiment theory cycle is not as simple as just it's not powered only through mathematical formalisms, which was what it was many decades ago, but rather machine learning and Bayesian statistics is embedded in that. And in nuclear physics in particular, because these are very complex phenomena and all of the other things that I already mentioned. And this has been recognized by the community, at least in nuclear physics. We sat down every 5 to 7 years and create this document that says, these are important things for the field. And in this particular document, we said machine learning and Bayesian tools are extremely important to advance further. Together with some friends, and aligned with this type of reasoning, we created this summer school last year that was about machine learning, emulators, and Bayesian statistics. We run it at EFRIP. And the reason why I'm pointing this out is because there is all the recordings of the lectures and the materials that we created can be accessed through here. So if you're interested and you were not able to attend, that is another way that you can learn about these things. Okay, so that was my nuclear physics introduction in 15 minutes. I'm going to go to the dimensionality reduction part. Let's try to motivate this. So imagine that I have some experimental data that I'm labeling there in blue. I don't know, some y that depends on x. Now, I want to create a model that can explain this data. This could be a cross-section or whatever the heck I am. I'm going to say that my model f depends on x and has some parameters alpha. And you might think that the idea will be, I want to, I don't know, fit the parameters alpha such that my curve explains the data in the best way, but the goats are watching us from the corner. We don't want to do that. What we want is to come up with an uncertainty, quantified way where I can give error bands and predictions around it. The way that I do it, and many people as well, we use Bayesian statistics that uses Bayes' theorem that I'm not going to go into details, but if you want to, we can discuss about it later. Basically, the thing that I want, which is a posterior distribution of my parameters given the data, is comprised of three things that I can calculate. One is the likelihood, that is basically what we think is a process that we think created the data. The prior, which are the previous knowledge that we have about the parameters, and something that we call the evidence that for most practical purposes is just a normalization cost. Once you have that, you're very happy and it makes sense. The problem is that if you wanted to run this type of posterior samplings, usually it takes thousands or millions of samples of your physical model for different values of the parameters to be able to actually create these posterior distributions. And if each evaluation takes 1 second, you need 2 months. And if each evaluation takes an hour, you need half a century to perform these 5 million calculations. And you might say, what takes an hour of computation? Many things. In particular, in nuclear physics, I could have processes that are trying to explain in a time-dependent framework collisions between nuclei, or calculations that involve fission. And those are many-body calculations that can be very, very computationally expensive. That is what motivates us to try to develop these I cannot believe it's not butter type of approaches in where I am going to replace my physical model or my posterior by something that is an emulated quantity or an approximated quantity. There are many things that you can use to do this type of approaches. You might have heard about Gaussian process and neural networks. I'm going to be focusing in a lot of the part of this talk in modular reduction, and I'm going to talk a little bit about normalizing flows at the end for posterior distributions. This method can be very data hungry, so I'm not saying this is going to substitute high performance computing, but it's something that can be built on top of that. This invites us to have a shift in the computational paradigm. So this is me creating a representation of what happened 300, 400 years ago with Newton. Newton was sitting next to the tree, and by looking at the apple fall and the comets and the planets running around the sun, he was able to say, I know how gravity works. This is very easy. I just have one master equation that explains everything. With that, he can make calculations, and he can make a model that can do the three things that a model should do: explain, predict, and build. Now, in the 21st century, this is us. We're trying to understand nuclear physics. Our models are not as easy as Newton's equations, are much, much complicated. And whenever I want to make predictions or use them to explain or to build things, I need to run them through these computer approaches that can take a lot of time. This is where the computational paradigm we suggest that should change. We should put, before you run your entire calculations, stick the dimensionality reduction part, in where you substitute your very complex models by these surrogate approaches. It can be a neural network, but it doesn't have to be a neural network. It can be other stuff that I'm going to explain in a second. And once you have trained this reduced order model, you can deploy it in commodity hardware, your laptops, high performance computing, cloud computing, and that's what then ends up becoming part of the models that are deployed for the community. The fact that we can have these things run much, much faster means that we can put them in cloud computing environments such that we can make it accessible for everybody, not only the people that have access to very high performance computing environments. And this is part of an effort that my friend Kyle Godby, one of the people that is responsible for at least half of the results that I'm showing, one of the efforts that he's leading in trying to create a future in where nuclear models, at least, are not defined by specific parameter values, but rather for a continuous calibrated process as soon as new data becomes available. This is what we're trying to walk towards with these tools. Let me give you an idea of how this will work. So you have your very complicated equations for your model. The equation itself doesn't matter. I just want to show you that it's a nasty equation that involves many things. These parameters alpha, you can think of them as the rules of the game that I'm going to try to change. And you may have a black box code that a poor grad student wrote 20 years ago. You don't want to look at it. It's just a computational box that from parameters it calculates cross-section. In this case, could be the probability of neutrons impacting on calcium-40 and deflecting by some angle. So you want to make this map faster to run. If you were to open the box, that you do not want to open, what you will see is that this thing is calculating a lot of quantities, intermediate quantities. And I'm making up a number. Maybe this needs to calculate 5,000 variables, wave functions in the middle of the thing to be able to arrive at these cross sections. What a reduced order model is trying to do is to say, I want to bypass this computational complexity and achieve something that is very similar accuracy-wise through something that might have like 100 variables instead of 5,000. And at the end of the day, we want to make sure that these two things, the true quantity or the high fidelity quantity and the one that we're estimating are as close as possible. And we usually characterize that through something that we call the computational accuracy versus time plot, in where the reduced order model has a much better trade-off between accuracy and speed. You're going to see this plot a lot. So for how to actually make this work is 2 steps. It's very easy. The first part, you need to find good reduced coordinates for your problem, and the second, you need to find equations for them. Let me use as an example a brick. Everybody knows that if you really want to understand what happens to a brick as it's moving through space, you need to look at the 10 to the 24 atoms that constitutes the brick and write equations for each one of them. Of course, we don't do that. You could say, for what I'm interested in, I could replace all of those degrees of freedom by 3 translations and 3 rotations. That will be more than enough. If the brick breaks, or if you want to understand sound propagation through the brick, you will need more degrees of freedom. But for what I am describing, this will be more than enough. My equations could be the Lagrange equations or Newton's equations of motions to understand how those 6 degrees of freedoms are evolving in time. In the case of actual models and differential equations, and I'm going to talk about in more details about that, one way of achieving that is through something that is called the reduced basis method, in where finding the reduced coordinates works in this way. You solve your problem several times, and you get a family of solutions. And from that, you could extract a principal. You can use a principal component analysis to find the reduced bases that now your coordinates are the amplitudes of these bases. I will explain that in more detail in a second. The second step of finding equations for them, you could use something that's called the Galerkin projection. This is Boris Galerkin, and we really like him, so he's going to be around the talk in different suits. And the way that this works is by projecting your operators into test functions. If you're confused about this, it sounds very intuitive. You can ask me at the end of the talk why, and I can point you to resources that might make this more accessible. Let me explain it with a specific example because I'm sure that nobody understood anything of what I was saying. Imagine that you have the quantum harmonic oscillator Schrodinger equation. In this, I have a parameter alpha that is controlling my trapping strength. So if my alpha is very small, that means that my wave function is going to be very spread. If my alpha is very big, that means that my wave function is going to be very concentrated in a single location. I could decide to say, you know what, I'm going to solve this equation by discretizing my space. And if I discretize my space, my function phi is a set of big N numbers. It's a very long vector. So I want to think of this solution as a very long arrow that is living in a very high dimensional space. Make sense? Very good. So now if I were to make many solutions for many values of the parameters, I will get many arrows in that high dimensional space. And now look at this very cool animation that I have for you. Are you ready? So if you were to have a continuum of solution as you change the parameter alpha, you will have what I call a solution manifold. It's just the trajectory of that very high dimensional vector as it's moving through space. Now, even though that is a high dimensional object, perhaps I can find a subspace that I can approximate that solution trajectory or manifold that now I can describe the approximation of this solution using way less dimensions than the object itself. I go from something that I need to specify 300 numbers to something that I only need to specify 2, which will be the coordinates in this plane. Those are the 2 reduced coordinates that I use from phi 1 and phi 2. Numerically, this will mean that I will expand my solution phi as a linear superposition of these phi 1 and phi 2, which are the 2 principal components out of my set of solutions. To make the equations, I grab my original Schrodinger equation. I write it like this, which is just a fancy word, a fancy way of just passing this to the left and saying that the entire thing is equal to 0. I project using the Galerkin projection idea. The details don't matter. What I want you to see is that I end up in a situation in where I have 2 variables that I do not know and 2 equations that I need to solve for. And this is what the reduced basis method is doing. Now this problem is much easier to solve. It's much faster. This is an animation showing how the actual solution of the harmonic oscillator changes when you change the trapping strength, and the approximation from the reduced basis method that I'm using only the superposition of these two. If you're looking at this and you're like, but my problem is much, much complicated that the harmonic oscillator, it will never work. There is a way in where you can, before spending too much time looking to see if this will work or not, check it beforehand. And that is by visiting what we call the PCA doctor. You go and you talk with her after doing a singular value decomposition of your solutions. If the singular values of your problem decay exponentially, that means that you're nailing it. This is a problem that you can use these techniques to track and solve it better. This is a bunch of resources that you can use to learn about how to implement these things. And this has been made by the community, for the community, with a lot of people. And the next person might be you, if you're interested in develop these things to any of these particular problems. I want to highlight that this person here, Megan Campbell, she's a high schooler that is working in San Luis. She is attending high school there, and she got interested, and that is going to be one of the final parts of my talking, how this is extremely accessible to a lot of people, including folks that are in high school. Okay, now I have 15 minutes to bombard you with applications, and then the final thing that I want to say about inclusion. So if I'm running out of time, I'm going to skip a couple of the last applications, and I'm going to jump to the next part. Let's all take a breath, because I have been monologuing for a long time. Okay, get ready for the bombardment of applications. First application, density functional theory. I know that a lot of you folks working in density functional theory for electrons. That means for material science and condensed matter. I am applying density functional theory to nuclear physics. Instead of modeling how every proton and every neutron in a nucleus interacts with each other, I'm going to make an approximation in where the nucleus is a blob and has an average density, and my protons and neutrons interact with this average density. I'm showing you this equation because I want you to say, ew, that looks extremely complicated. And on top of that, all of these things that I'm highlighting in purple are parameters. So this is a really complicated problem. This is not the harmonic oscillator. This is not your average easy textbook example. Nevertheless, the singular values of this thing, DFT, calcium 48, decay exponentially. So this should be applicable. And in this first paper, we show that this method is amenable for a broad class of problem, density functional theory included. We tested, and this thing is extremely accurate, to the point that this figure got me in trouble with the referee because they didn't believe that what we were doing made sense. Let me explain. In here, I'm showing L is one of the parameters that I'm controlling one of the alphas, and this kappa is another parameter that I can control. And we're looking at the neutron spin thickness, basically the difference in distribution between protons and neutrons, as I change these two parameters. This reduced order model, or emulator, we train it within these red box in here, in these 4 stars. That is the only thing that this emulator was able to see, and is able to predict the entire behavior with very, very little loss in accuracy. So the referee didn't believe it. He's like, no way, because they were thinking that I was fitting the data in this plot. And he's like, no, there is a lot of high dimensional stuff that is happening behind the hood that you don't see when you see the plot. And it's extremely fast. We were able to run calculations of DFT that usually takes seconds. This was a spherical DFT and relatively easy to run in milliseconds. So something between 2 and 3 orders of magnitude of speed up. The second application is density functional theory, but the relativistic mean field approach, a different type of flavors that you can use to reproduce these things. These are the Dirac equations. The equations don't matter. These are relativistic equations for your protons and neutrons that are interacting in this way. And the reason why I'm showing these equations is because my dog name is Dirac. And I usually try to find an excuse to put him in my talks. But if you see the equations, you see all of these things in here are parameters. What do you do with the reduced basis method? You just project with Galerkin, pew, 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 and you have projected your equations, and everywhere in you see your incognitas, your fields, and your wave functions, you just replace them by the reduced basis expansion. Once you do that, you get what the goats wanted. You're able to do Monte Carlo sampling and estimate posterior distributions in a single day. We run 5 million samples in 1 day in that laptop. This is mega fast. This would have taken 5.5 years to run if you were running it in the traditional ways. You end up obtaining speedups that are between 1,500 to 25,000 times faster than the traditional way of solving this. And with that, we were able to make predictions. One of them in particular is the charge radius of one of the thin isotopes. which doesn't matter that much, but I just want to brag and say that is something that people at Efrit could measure, and it will be a prediction from our new models. A second application, a third application is how you use these things to produce a relationship between masses and radii of neutron stars. That way you can actually link together nuclear physics and astrophysics. And you do that by solving something that is called the Tolman-Oppenheimer Volkov equation. And that Oppenheimer is the same Oppenheimer from the movie, if you watch it. One interesting thing in here is that if you look at your solutions, you plot them, you visit the PCA doctor and she will tell you, no way that you're going to be able to combine all of these things in the way that you want. So one of the neat tricks that we were able to do is by scaling these things together, now putting them in a single plot, by scaling by the radius of the neutron star, you're able to actually make an emulator that is able to solve the problem. And then we have cosmonaut Galerkin in his suit for space. Application 4, I guess, reactions. You want to shoot particles, projectiles into a target. That is very important for Efrit. And here we have Galerkin with a rose. You will see why in a second. This is my Schrodinger equation for scattering. The equation doesn't matter. The point that I want to make, in this thing in here, this potential is the potential that has the rules of the game. And I want to change those rules and see how the interaction between my projectile and target changes. Through the collaboration that I was part of, we created this software which is called ROSE. That's why Galerkin has a ROSE, which is called the Reduced Order Scattering Emulator. And this is a map of what the emulator is doing. The main point is that you do not need to understand this because it's a software made for people. So if you're interested, you could, but it's not something that you need to in order to use the software. This is a cat plot showcasing how this works, and you see the difference between the high fidelity solver, the usual traditional approach of solving things, and the reduced basis method, which ends up being 2 to 3 orders of magnitude faster. And with this, we're able to predict cross-sections with uncertainties as the goat would have wanted. This is extremely important for facilities like Efrit, in where if you're trying to understand what happens in collisions for very rare isotopes, many of the theoretical models that we have available have been calibrated to stable isotopes, the boring ones. So if you're going to extrapolate this thing that was calibrated only on the black points all the way up to here, you need to estimate your uncertainties or you're going to be screwed. So this is just highlighting that this is a very easy to install software, and it has tutorials. And if you're interested in how this thing works, all the links are there available. Application 5 or 6, dynamics. You can use this also to study the time-dependent propagation of systems. In this case, I'm showing again the quantum harmonic oscillator. And basically what happens is that instead of having to evolve your system in the big dimensional space, you reduce it to a low dimensional space, you evolve in there, and you're able to reconstruct your wave functions. And once again, the cat plot is showing that the reduced basis method completely outperforms the way of solving this in a traditional way. This is very similar to something that is called dynamic mode decomposition, dropping the name in case you have heard about it or you're interested on it. This is yet another application. In here, we're not using the reduced basis method. This is using a neural network, and this is developed by a couple of people that I'm going to be talking about in a second. The interesting thing in this is that this neural network is learning the nonlinear dynamics, in this case of a vibrating nucleus. And this is extremely cool because this can be used for model discovery. But when you have data, you don't necessarily have the equation, and you're trying to create a model that actually is able to reproduce these things. This person that developed this with me and Kyle, Aaron Phillip, he's an undergrad working with us at the lab, and he was able to get an award at a fair at Michigan State, and we were able to take him for ice cream for that. That is the whole reason why I do physics. This particular implementation was not invented by us. It was invented by these two folks that I'm the president of their fan club. They have this amazing book and an amazing website where they guide you through videos on how to apply these type of things. I'm going to share all the links because it can be very useful for you in the future. Now, I have 10 more minutes. I'm going to talk about one more thing that I don't want to go over the details, but remember that I was mentioning there's 2 steps in here: finding good reduced coordinates and finding equations for them. The problem with everything that I have been showing you so far is that you need to be able to access these equations. These require that you can see the equations. So if you have something that really looks like a black box, or it's an experimental setup where you do not have the equation, you actually cannot implement this in a very efficient way. One of the directions that we're trying to explore is, can I learn the second step as well directly from data? Basically, instead of doing the Galerkin projection, just feed a reduced system of equations from data that I obtained. To put it, and we have Galerkin in the lab house because that is cute too. This is related to some work that other folks are doing, but to put it in a concrete example, imagine that I have a situation in where I'm passing a beam of particles through a bunch of magnets, and I'm changing the currents on each one of these magnets to try to get the beam to the target that I'm interested in. I do not have necessarily an equation, but I will still like to obtain a reduced model that can mimic this thing very fast. And the first exploration that we have been doing about this actually shows that yes, you can, and you obtain something that is way faster than the state-of-the-art computations that you can achieve using normal ways. Okay, let me take a breath. I'm going to talk about one more application, and then I have 5 minutes to close. Normalizing flows. This is important, and it could be important not only for people doing Bayesian posterior distributions, but if you're working on any distributions of any kind, and I know that some people working with Monte Carlo, quantum Monte Carlo samples, find this type of techniques very useful. So this is a target posterior that I might have. This is showing just the probability distribution of some of my parameters, alpha 1 and alpha 2, and the maybe nonlinear correlation that I might have between the two of them. The idea of the normalizing flow is saying, what if instead of having to describe my posterior distribution by the samples that I visited on each step, I describe it by looking at boring Gaussians that are uncorrelated boring Gaussians, and I find a map that maps you from this space to this space. We do that through a neural network, and now the posterior distribution that you're interested in is encoded in the neural network. And this is a different way of doing dimensionality reduction. I am not describing my object by the millions or thousands or tens of millions of samples, but rather through the weights of the neural network. We have been applying this to many of the problems that I have showcased in here, and in the plot you see in red and in black the approximated one and the true distribution, and the thing seems to be working extremely well. And this is one more step in the dream that Cal has of having this continuous calibration of models as new data becomes available, because now every time that our experimental friends measure something, I don't have to run the entire Monte Carlo again. I just need to update the neural network, change the weight slightly to reproduce the new data. I'm not going to talk about this, but basically the idea is that you can use these same ideas to combine models if you want to combine the predictions of models. If anybody's interested in this, I'm more than happy to talk, but I don't want to bore you with this. So I'm in the final part. Let me breathe again. I want to talk on how we can use many of these tools to lower the barriers for more people to join the scientific endeavors. The reason why I envision that this is possible is threefold. Statistics, and I'm calling statistics, but you can think in terms of data science and machine learning. The first part is that it's something that is widely applicable and highly transferred. There are some studies that show how people that end up learning these skills can actually work on an insane amount of parts, both in academia and in industry. It's almost self-trainable. There's a lot of resources out there online that allows you or whoever is interested in this to just learn it by yourselves with actual applications to serious problems. And three is something that is exponentially impactful. This is a very funny article that is using machine learning to try to predict how many future papers are going to be using machine learning in the future, and it's an exponential trend since 1980s, 1990s. So with this, I believe, as well as many people, that this is a perfect opportunity for creating a more inclusive scientific community. And that is one of the main recommendations from the nuclear community that I was talking about, in where we want to draw the talent from everybody in the nation and more generally in the world to help us with these problems. That is one of the reasons that has motivated me and my friend Cal to create the Ascension Network. Somebody was mocking me and was saying, it's the Ask a Nerd network, but no, it's the Advanced Scientific Computing and Statistics Network. And because Kyle is a magician, I really don't know how he's able to make this. He was able to put out together a forum when people can ask questions, formulate problems, and collaborate together. And we have been using this for a lot of things, including the summer schools that we were running last year. And I'm using it for the classes that I'm teaching as well. We have also created the Ascension Scholars Program, where, by the way, I made these are many of my images with ChatGPT. What I wanted to evoke in here is this feeling that I have that a lot of folks in high school have a lot of time in their hands, a lot of energy. We just need to find a way of analyzing that to create something that is useful for them and then for us. So we created this program, and we're piloting with the PING program. Paul Gay was, I think, making the colloquium, giving the colloquium a week or a couple of weeks ago. And we have gathered a group of high schoolers. We're running the pilot program, and in there, these are two of these programs, Physics of Atomic Nuclei, that is fun, and this is pink. The idea is that we're exposing them with career talks on what you can do once you make a study in physics or some other academic careers, giving them materials and tools from statistics and computationals, and we are creating a research project. There is 5 of them, Megan, Omjas, Emma, Shuri, and Shiria, that are actually writing a paper with me and Kyle, and another friend from the LIGO collaboration, that is a serious paper exploiting many of these things applied to nuclear physics. And I am just amazed by how quickly they learn. They are solving differential equations in Python, writing code in a pedagogical way, and applying these machine learning tools. And all that it took, they're not particularly brilliant, but all that it took was a good environment to foster that collaboration that they have between them. So, my takeaways, if I have put you to sleep in the previous parts of the talk, these are the 2 things that I would like for you to remember. The first one is that these methods, statistics and machine learning in general, are propelling science towards a new era of discovery. And there is no time to waste, so we really want to pass through as fast as we can and reduce the dimensions of the useless part. And the second part is that it's something that could help propel science towards a new era of inclusion, where we're not lowering the barrier, but we're rather just destroying it. A timing where everybody is welcome at the table. So with that, I am going to put my thank you slide in where I thank the people who have paid for my lunch, my amazing friends and collaborators, my awesome host, Sibi, all of you for listening, and I leave you this with a lot of resources that you can use. Thank you.